Okay, so this is a segment for lecture 4 about doing examples. So we've seen binary phase diagrams now, and what we're now going to do is look at using those to do problems. And it's worth thinking about, why bother doing examples? Why do we do this? And the main reason is the science ideas are useful insofar as we can apply them to solving problems. And quite often we find that we think we understand the theory and you think it all makes sense, but then when you try and do a problem, it goes wrong and it doesn't quite work and you're not quite sure what's going on. So it's quite often hard then to articulate, especially when you haven't been studying on your own for very long, what we don't grasp about a concept. And when we try a problem, we find out that, okay, it's not quite working. We don't quite understand it right. And problems help us illuminate, if you like, what we don't get. So the role of a lecturer or tutor is to come and say, so the reason you're having a problem there is probably that you don't understand this very clearly. And that's difficult with a big class, right? So what we're trying to do in peer instruction is we're trying to shortcut that and look at how we understand what we don't understand and what the conceptual difficulties are and how we get over them. So Feynman talked about this on understanding physics physically. He was teaching physics to undergraduates. And what he said about that was, so those are all the rules I can remember as being necessary. He was talking about all the rules for doing little mechanics problems. And what he was concerned about was this. He said, so you say, I'll memorize them, all the rules, and then I'll know all the physics. And he said, well, that won't work. And what he said was the problem of how to solve problems is really very difficult to teach, and I don't really know how to do it. This is a guy who won a Nobel Prize. What he said was, I don't know how to tell you something that will transform you from a person who can't do problems or analyze new situations to a person who can. And he said, because I intuitively understand what's going on physically, I find it difficult to communicate. I can only do it by showing you examples. So he said, the ancient Babylonians had no way of understanding formulae. Instead, they did one example after another. That's all they did. The idea was you're supposed to look at the examples until you get the idea. And Feynman then said, today we don't have the power of expression to tell a student how to understand physics physically. The only way is to follow the old Babylonian way of doing problems until you get the idea. So that's all I can do for you. And he said, moreover, the students who didn't get the idea in Babylonia flunked, and those who did died. So, it's all the same. So he was making a philosophical point. But yes, you have to do an exam where you solve problems. But it's not about just plugging numbers into the equations and memorizing how to plug the numbers in and solve the problems. The idea is to turn you into somebody who can solve problems, new problems that you haven't seen before. So it's quite different at university to at school. At school, you memorized how to solve the problems and then applied that in an exam. In real life, after university, somebody's going to ask you to solve engineering problems that nobody's ever solved before. We've never built a jet engine quite this way before, for instance, or, what's going on here. And you're going to take the science that you've learned at university, and that's going to give you the platform on which to figure out how to solve the problem. And our exams are trying to replicate that process. So we're not interested, actually, in you solving problems that you've seen before, but with different numbers. We're interested in you figuring out how to solve new types of problems. So it's a new way of learning. It's a new thing you're trying to do. But in what we're doing here is we're starting that process. So we're starting to look at trying to apply the theory we've done so far to solve some problems. So we're going to start doing that. Mostly that's in the tutorial questions, but we'll start doing that now for a few examples just in binary phase diagrams. So we're going to do an example with the aluminium silicon phase diagram here. And before we look at the questions, which are on the sheet, which are in the notes, then we can look at this diagram, which I've copied out, and you can see a couple of phases here. You've got liquid, which seems to have complete solubility. You've got an alpha aluminium phase there that has limited solubility for silicon. That's pure aluminium with a bit of silicon in it. So we call that alpha aluminium. And we've got a phase here, silicon, which is over at 100 weight percent. It's by convention because we're just calling it silicon. We're not giving it a letter. It doesn't have any solubility at all. And we're given 3 points, this one, and this one, which we'll use as we go around using the diagram. And otherwise we'll have to measure in order to see what's going on. So the first question is, what's the maximum solubility of silicon in aluminium? So what's the maximum solubility of silicon in aluminium? So the first question is, which phase is aluminium? Well, it's this one. It's the one that forms with pure aluminium. So it's the alpha phase. And the maximum solubility that you ever see is at this point here. That's this point just there. That's the maximum amount of silicon you can ever get into alpha aluminium. It occurs only at this temperature, 577 degrees, and that's the maximum solubility you can ever get. So if we want to know what that solubility is, then we have to find out what that corresponds to when we drop down onto our axis here. So we have to drop down onto this axis and find out what this number is. Now, to do that, we're going to have to do some measuring. So I have myself a convenient ruler here. So if I look at my ruler in a reasonable way, then this is a distance of 3.2. From 0 to 5 there is 3.2. And that distance there, that horizontal distance, that's a distance there of 1.2. So that distance there is 1.2 out of 3.2 times 5 weight percent. So that's 1.2 divided by 3.2 divided by 5. So if we go and work that out, we go and get a calculator. So I have my calculator. This is the calculator used in exams. Divided by 3.2. That's 0.375 times 5. That's 1.875 is what my calculator tells me, but I'll call that 1.9 weight percent silicon. Now, there's a couple of things to say here. I've used a sensible amount of precision for what I can sensibly measure off my diagram there. I haven't gone and said 1.875, which is what my calculator tells me for that sum. I've rounded it off to what I think I can sensibly measure, and it's certainly no better than 1 decimal place. It's probably not even that good. I've also put the units in, weight percent silicon. I haven't just left it with no units. And if you don't put the units in, there's a simple rule, you don't get the marks. Okay? So that's the maximum solubility of silicon in aluminium. The next one is mark the eutectic point. Well, the eutectic point is this one. It's the one temperature where liquid transforms to 2 phases directly. So the last liquid here would transform directly to alpha aluminium and silicon. So that's the eutectic. We'll mark that on there. That's the eutectic. And if you wanted marks, again, you would have to write eutectic in the arrow rather than just putting an X somewhere at random. What is the maximum solubility of silicon aluminium at 300 degrees C? Well, that's down here. So it's only just greater than 0. So at 300 degrees C, so that's question 3, at 300 degrees C. Well, again, it's going to be some small amount here. So this small amount here, this little amount there, that's a distance of about 0.1, 0.2, something like that, 0.1. It's a small number. So that's 0.1 out of this whole distance of 5 weight percent, which corresponded to 3.2. So that's whatever that is. It's a small number. 0.1 divided by 3.2 times 5. That's 0.15. Let's call it 0.2 weight percent silicon. It's quite a small number. Yeah. So the solubility is not 0. Notice it might go all the way to 0 at 0 degrees Kelvin, but it's not 0 at 300 degrees C. There's a little bit of space there. The next question 4. What's the melting point of pure aluminium? Well, if I take pure aluminium, it's solid alpha all the way until it transforms to liquid at this point here at 660 degrees C. So that's 660 degrees C. Next question, 5, is about an aluminium 1% silicon alloy. So we'll start looking at a aluminium 1% silicon alloy. So that's aluminium 1% weight silicon. And we're going to ask ourselves some various things about that alloy. So we better mark this on the diagram and see where it is on the diagram. So I said this distance along the bottom, that was 3.2. So I want a fifth of that distance. So it'll be at a fifth, so that's 1 out of 5 weight percent, times my distance of 3.2 that I measured. And that's a distance of 0.64. So I've got to mark 0.64 on. So let's do that in a couple of places. 0.64, that's something like there. 0.64 is something like there. And we're going to put a ruler on. And we're going to mark our line. And we're going to do it as accurately as we can. So that's my aluminium 1% silicon alloy there. So the first question, question 5, if you like, the first question in this little series about the aluminium 1% silicon alloy is, at what temperature would it begin to melt? Well, if I heat it up, it enters the pure alpha region here, and at this point here, it starts to enter the alpha plus liquid region. So that point there is the point at which it starts to melt. This point just there. So at X, if you want to put a number on that, that would probably be desirable. We need to work out where that is. It's somewhere between 600 and 700, look. So we could measure it. So let's think about that. So what would you do? Well, you'd say, well, 100 degrees C, that's a distance of something like 4.5 there. So 100 degrees C corresponds to 4.5 on my ruler, whatever my ruler's measured in. And the distance above 600, if I come across to here, measure that, that's a distance of 1.1. So I've got 1.1 divided by 4.5 times 100 degrees. So about a quarter of 100 degrees, something like that. Let's calculate the number. 1.1 divided by 4.5. So that's 24 degrees. So that's 24 degrees above this number. That's 600 degrees C. So that's 25 degrees C. So it's 25 degrees C above 600, which is about 625 degrees C. And that's one way of answering the question. Now, we said that this, when we did part A, we said that was 1.6 weight percent silicon. And the other way to do it is to say, well, okay, if I assume this line is a straight line, that's an assumption. If I assume it's a straight line, I'm about 1 divided by 1.6, well, I'm exactly 1 divided by 1.6 of the way across here, which means I'm that fraction down here. So from 660 to 577 is some number of degrees, so that's 83 degrees equals 83 divided by 1.6. And I'm that far below 660. So 83 divided by 1.6 is 52 degrees. And so my temperature will be 660 minus 52 degrees C, which will be something like 608 degrees C. So I get a bit of something like a 10 degree difference on that, and that's probably reasonable. I'm not very accurate. I'm assuming that this is a straight line, and it's not drawn as a straight line, but that's a reasonable assumption. So there's two different ways to answer that question, and they give you slightly different numbers. Now, if you were in an exam, you would say, well, measuring from the graph, then I'm this far down, therefore it's 25 degrees above 600 there. Or you would say, well, assuming the phase boundary is a straight line, then I'm so far below, so I'll be 52 degrees below that point of 660 degrees C, and you get another answer. Either will do, but you need to tell me, to get full credit, how you arrived at that answer. So the next question would be, at what temperature would solid first form from a melt of this same alloy? So if I'm taking a melt of this same alloy, well, it's liquid all the way down to this point here, right? That temperature there. And that's just a little bit below 660 degrees C. So that'll be some amount just below 660 degrees. So again, if I'm thinking about measuring it, I'm 1.6 out of 12.6. So it'll be 660 minus 1.6 divided by 12.6. I'm that amount along this line here. If we assumed it was straight, well, it declines from 660 to 577. So again, that's my 83 degrees. So then what I'm saying is that the gradient of that line, of this liquidus line, that will be divided by 12.6 times 83. That'll be about 10.5. This gradient will be about 10.5 degrees C per weight percent. So that's, sorry, no, that's not quite right. That's just 10.5, even, once I multiply it by 83, minus 10.5. So the gradient isn't quite that, sorry. What it is the gradient of it is 660 minus 5, so it's 83 divided by 12.6 weight percent. So the gradient of it is 83 divided by 12.6. So it goes 6.5 degrees C per weight percent. What have I done? I've got myself in a terrible mess. Yes, because I've gone for that alloy, not right. Dope. Okay. You're going to have to black screen me for a moment and stop. I'm not going back and doing all that again. So question 6 is, what happens with this aluminium 1% silicon alloy? When does it first begin to solidify? So if we take a melt of it, it starts off as a liquid up here, and it then hits this liquidus line at this point here, this point there. So when will that be? So we can look at what the gradient of this line is. We could measure it, but this is a possibly more accurate way. You take your pick. But if we assume this is a straight line, then it has a gradient. It declines this 83 degrees from 660 to 577, that 83 degrees, over 12.6% in weight percent. So that declines by 6.6 degrees C per weight percent. That's the gradient of that line if you assume that it's straight. So we're in an aluminium 1% silicon alloy, so it'll start to solidify when it hits that line. That's at 660 minus 1, so our alloy content, times that gradient, which is 6.6. So that's at 653 degrees C. If you say that's about 7. That's about 653 degrees C. That's when solidification will first start to occur and you'll first start to form solid. The next question, question 7, is what's the composition of the first solid to form? Well, it's over here. it's at the solidus line. So it's over at this location over here. So again, that's a small number. It's not going to be a very big number. And we've got to think about, well, okay, how do I calculate that? Again, you could just measure it, yeah? And if we measure it, then we get our ruler out and we say, well, that's about something like 1 or 2. 2 out of this number here, which was our, wherever it is, out of our 3.5 or something. What did I measure that to be? 3.7. So that'll be about 2 out of 3.7. So question 7. 0.2 out of 3.7 times 5 weight percent. So it's a small number. 0.2 divided by 3.2 times 5. It'll be about 0.3 weight percent silicon. The other way to do it is we could say the maximum solubility was 1.6, and we've gone 1 divided by 1.6 of the way along that way, which means we've gone at 1 over 1.6 the way down that way. Oh, no, we haven't, sorry. The other way to do it is to go and say, well, okay, at 653 degrees C, at 653, then where is this line? Well, it goes from 0 to 1.6 over the course of that 83 degrees. So that line, we can calculate its gradient. So if we say it goes so many degrees C per weight percent, so it goes 83 degrees C over 1.6 weight percent. So it goes at a gradient of, it's going to be something like 50. 83 divided by 1.6, right, 52 degrees C per weight percent. That's the gradient of this solidus line. We want to go 7 degrees down to 653. So we're going 7 divided by 52. So that's degrees C by degrees C is equal, gives us something in weight percent when you divide those two. So that's 7 over 52, and that gives us an answer of 0.14 weight percent silicon. And that's probably a more accurate answer. Either way, it's a small number. You can do it either way, whichever way you prefer. And the last part of question 7, what's the composition of the last liquid to solidify? Well, the last liquid to solidify is over at this composition. So when we go and find out what that temperature was, so we found that temperature was 605 or 608 or 625. We come over here and drop down, and you can see it's going to be something like 6 weight percent. And again, you would measure it off the graph. You would say, well, that distance there from the axis all the way over, that's about 4.1 out of my, whatever it was, 3.7. So that's 4.1 out of 3.7 times 5, and that's going to be a little bit more. So if I say 4.1 divided by 3.7 times 5, that's going to be 5.5 weight percent, in fact. So that's the composition of the first solid to form, calculated 2 different ways, and that's the composition of the last liquid. And we've only calculated it one way, but you could do it the other way if you wanted. By now, you're hopefully starting to get the idea. So then, as the casting is then cooled further, what would then happen? So, and sketch the resulting microstructure. So it's all been liquid. We've come down into the alpha plus liquid region, and now we're in the solid alpha region. So what would we expect to see as a microstructure? Well, let's sketch it. So sketching it, that's our field of view, and we'll say, well, we'll have some grains in here, and they'll do something, I don't know, like that. and they'll all be grains of alpha aluminium. That's what it'll be all the way down from that temperature all the way down to here. And at here we'll start to precipitate, we'll come into the alpha plus silicon region, and we'll start to precipitate some silicon. So I'll put in some little bits of silicon on the grain boundaries. Some at the triple point here, some silicon there, and we'll label them as precipitates. PPT is the abbreviation for precipitates of silicon. So that's the microstructure we would expect to see as we cooled that aluminium 1% silicon casting. So then questions 9 and 10 are about an aluminium 5% silicon alloy. So if we're considering an aluminium 5% silicon alloy, the first thing we better do is draw it on the diagram. So where's our alloy? It's somewhere like there. So we'll draw it on the diagram. So there's our aluminium 5% silicon alloy. And the first question 9 says, when it's slowly cooled, what phases would you expect to observe at 578 degrees C? In what fractions and with what compositions? So at 578, we're just above this line corresponding to the eutectic. So we've come down from the liquid and we've formed alpha aluminium plus liquid, and now we're just above that point. So that's our alloy, 5% silicon. So here at 578, we're just in the alpha plus liquid regime. And the composition of the alpha will be over here, so that'll be 1.6 weight%. So we'll have alpha aluminium at 1.6 weight% silicon. And we'll have liquid, which is over here very nearly at the eutectic point, which will be at 12 weight% silicon. And if we want to calculate the volume fraction, those are the two phases, those are their compositions, and if we want to calculate the volume fraction, we could say, well, the volume fraction of alpha is the opposite little distance divided by the whole distance. So the volume fraction of alpha from the lever rule is the opposite little distance, that's 12.6 minus 5, divided by the whole distance, and that's 12.6 minus 1.6. So then we've just got to work out that, so that's then 7.6 divided by 11. So 7.6 divided by 11, that's 69%. So that's our volume fraction of alpha phase. That's question 9 done. For question 10, what happens to the remaining liquid at 577 degrees C? Well, this liquid that's left, that undergoes the eutectic transformation. So we've solidified to that point. We've got alpha here. So our micrograph would look, let's draw it up here. We'd have crystals of alpha. We're not asked to do this, but we can. And they compose about 70% of the volume fraction. And there's some liquid in between. And what's that going to do? That's the question. Well, it's going to transform here to alpha plus silicon. That's what happens at the eutectic point, is you have a transformation from liquid to two solid phases. Then we need to, the question is, find the fractions and compositions of the microstructural constituents. So this last liquid that was left, it's transforming to alpha plus silicon. And we said that those quite often formed as plates. So that's something like this. So we'll say that's a eutectic of alpha and silicon. So in the eutectic, then what will happen? Well, we've got a volume fraction of alpha and silicon. So in the eutectic, the volume fraction of alpha will be, we've transformed this liquid into alpha and silicon. So we've got, if you want to know the volume fraction of alpha in the eutectic, then it's the opposite little distance. So that's 100, because the silicon's all the way over there, minus the liquid composition, that's 12.6, divided by the whole distance, which is 100 minus 1.6, because that's our solubility in the alpha. So that's, whatever that is, that's 87.4 divided by 98.4. So we can work out that. 87.4 divided by 98.4. So that's 89%. So overall, we've got alpha primary, and that's 69%. And we've got alpha in the eutectic, and that's 89% of the remainder. So that's 89% times 0.31. So that's 89% times 31%, which is 27.5%, or we'll call it 28%. And then we've got silicon in the eutectic, and that's going to be 11% of the eutectic. So we've got 11% of the eutectic times the 31%, which is something like 10%. 11% times 0.31, so that's 3.4%. And in total, what have we got? We've got 69 plus 28 plus 3, that adds to 100. So overall, that will work out within rounding error. So when you see the term microstructural constituents in a question, what it's meaning is both the phases and the forms in which they occur. So for the alpha, whether it's primary alpha crystals or alpha in the eutectic. If you just said to me, well, the total amount of alpha from the lever rule is 97%, and the total amount of silicon, well, I'd say I give you partial credit. You've shown me you know how to use the lever rule, but you haven't understood, or you haven't demonstrated that you understand how to divide it into constituents. That is this primary alpha and alpha in the eutectic there. And so that's a quick whiz round the sorts of questions that you can ask with phase diagrams and answer using them, and the sorts of calculations you can do.